Welcome to Chapter 2. In Chapter 1, we learn what statistics are and why it matters. Now we're going to learn how to actually organize and summarize data using frequency distributions, tables, and graphs. These are the fundamental tools of descriptive statistics that we introduced last time. This chapter will cover the following learning objectives. Let me start with a scenario you can all relate to. Imagine you just got back your first statistics exam and you scored 80%. How do you know if that is good? You'll need to compare your score to everyone else's scores. If I showed you a list of all 25 students' individual scores, 80, 72, 59, 64, 90, and so on, you'd have to scan through every single number to figure out where you stand. That's time consuming and very confusing. But what if I organized that data into a summary table showing 3 students scored 90 to 99, 5 students scored 80 to 89, 6 students scored 70 to 79, and so on. So now you can instantly see that you're the second highest group. That is the power of summarizing data. So why summarize? Summarizing data makes the presentation and interpretation of data clear. For larger data sets, it can reveal patterns that would otherwise remain hidden in the raw numbers. In behavioral research, we often collect hundreds or thousands of data points. Without summarization, we would be drowning in numbers with no way to see what they mean. Think about how grades work here at Albany State. Your individual assignment scores get summarized into a course grade, and your course grades get summarized into a GPA. Each level of summarization makes it easier to understand your overall academic standing. A frequency distribution is a summary display for a distribution of data that shows how often or frequently a category, score, or range of scores occurs. Frequency distributions are particularly useful when researchers are measuring counts of behavior. When researchers find the frequency of values by counting the number of times scores occur, they can begin to see themes or patterns in the data that were not visible before. Consider research examining the time that children 8 years or younger spend using electronic devices. When the average time spent by 50 healthy children is just listed in minutes, it's not very informative. We need a more interesting way for someone to learn about children's use of electronic devices. The data obtained from those 50 children can be made much more meaningful by summarizing how often scores occur using a simple frequency distribution. There are 2 main types of simple frequency distributions, depending on your data. If you have a small number of possible values, like the number of children in a family, 0, 1, 2, 3, 4, and maybe 5, you can list each value individually. This is called ungrouped data. But when you have data with many possible different values, like screen time that could range from 0 to 200 plus minutes, listing every single value would create a table that's too long to be useful. Instead, we group the scores into intervals. An interval is a range of values. For example, 0 to 17 minutes, 18 to 35 minutes, 36 to 53 minutes, and so on. Each score falls into exactly one interval, and we count how many scores are in each interval. The key insight is this: with large data sets containing many different values, it's generally clearer to summarize frequencies in groups or intervals rather than listing every individual value. If I want to create a frequency distribution for students' ages in this class, would I use grouped or ungrouped data? I would use ungrouped data. Ages probably range from around 18 to 25 with only a few distinct values. There are 3 steps to construct a simple frequency distribution for group data. Number 1, find the real range. The real range is one more than the difference between the largest and smallest number in a data set. Number 2, find the interval width. The interval width is the range of values contained in each interval of a frequency distribution. You divide the real range by the number of intervals you want, typically between 5 and 20. Step 3, construct the frequency distribution. Create the interval starting with the smallest value and count how many scores fall into each interval. Your textbook walks through this process with a very detailed example. This slide illustrates a completed frequency distribution using the 3 steps we just discussed. Your textbook provides additional examples that walk through each step in detail. There are 4 important rules for creating a simple frequency distribution. First, each interval is defined by a lower boundary and an upper boundary. Second, each interval must be the same width, which we call equidistant. Third, no interval can overlap, meaning the same score can never fit in more than one interval. Fourth, all values are rounded to the same degree of accuracy as in the original data. The sum of all frequencies in your distribution should always equal the total number of values measured in your data set. This is an important check. An open interval is an interval with no defined upper or lower boundary, such as 125 and above. This can be useful, but it also means some descriptive information is lost. An outlier is an extreme score that falls substantially above or below most other scores in a data set. Outliers can sometimes be placed into open intervals. While the frequency of scores in a distribution can be quite informative, there are other ways to describe data as well. We can describe data aggregated across the intervals as cumulative frequencies, or we can express them as proportions or percentages. The rule of thumb is to always summarize data in terms of how you want to describe it. For instance, when a researcher wants to describe the frequency of safety complaints in discrete intervals, then a simple frequency distribution is a great way to summarize the data. But when researchers want to describe frequencies at or above a certain value, or the percentage of people scoring at least a certain score, then it's better to summarize frequency data cumulatively or as percentages. A cumulative frequency distribution is used when researchers want to describe frequencies above or below a certain value. It's a summary display that distributes the sum of frequencies across a series of intervals. Frequencies can be added from the top or bottom, depending on how the researcher wants to discuss the data. To illustrate, consider a researcher collecting data on employee safety by recording the number of complaints filed at 45 small local businesses. The researcher might use criteria to categorize businesses as safe, fewer than 72 complaints, at risk, between 72 and 89 complaints, or dangerous, at least 90 complaints. The bottom-up approach involves summing frequencies starting at the bottom and adding up. This is most meaningful when discussing data in terms of less than, at, or below, or at most. The top-down approach involves summing frequencies from the top and adding down. This is less common, but more meaningful when discussing data in terms of greater than, at or above, or at least. A relative frequency distribution distributes the proportion of scores in each interval. To compute a relative frequency, divide the frequency in each interval by the total number of scores counted. Relative frequency is particularly useful when summarizing large data sets or when comparing groups of different sizes. To convert relative frequencies to relative percentages, simply multiply each relative frequency by 100. Both summary displays convey the same information, just in different formats. The sum of all relative frequencies equals 1.00, and the sum of all relative percentages equals 100%. This slide shows how relative frequency and relative percentage are calculated and displayed. Your textbook provides the detailed calculations for the business safety example. A cumulative relative frequency distribution is a summary display that distributes the sum of relative frequencies across a series of intervals. To create one, you add each relative frequency, either from the top or from the bottom. The total cumulative relative frequency will always equal 1.00. With the bottom-up approach, you sum the relative frequency in each interval as you move up the table. With the top-down approach, you start adding from the top of the table and move down. A cumulative percentage distribution is a summary display that distributes the sum of relative percentages across intervals. The addition procedures are the same as with cumulative relative frequencies. The total cumulative percentage will always equal 100%, give or take minor rounding errors. A percentile point is the value of a score on a measurement scale below which a specified percentage of scores in a distribution fall. The percentile rank is the corresponding percentile of a percentage point. It's the percentage of scores with values that fall below a specific score. To identify the position or rank of an individual, researchers convert the frequency distribution to a cumulative percentage distribution. This cumulative percentage distribution is then used to identify percentiles, which are measures of the relative position of individuals or scores within a larger distribution. For example, the 75th percentile point is the value below which 75% of scores in a distribution fall. The 75% is the percentile rank. There are 4 steps to find the percentile point in a cumulative percentage distribution. Number 1, identify the interval within which a specified percentile point falls by looking at your cumulative percentage column. Step 2, identify the real range for the interval you've identified. Step 3, find the position of the percentile point within the interval. To do this, find the distance of the percentile from the top of the interval and divide by a total range width of that percentage. Then multiply that fraction by the width of the real range. Step 4, identify the percentile point by subtracting your step 3 result from the top of the interval. Your textbook provides a detailed worked example of this process. A pictogram or pictograph is a summary display that uses symbols or illustrations to represent a concept, an object, a place, or an event that typically corresponds to or reflects the data being reported. The benefit of using pictograms is that they help relate frequency data to images that correspond to or reflect the reported data. This helps bring to life or illustrate the data in a clearer way. Think about how data presented on a dashboard in a car helps you make sense of the information quickly, such as your speed. Pictographs are often seen in magazines, newspapers, government documents, reports, and even some research journal articles. For example, in the academic journal BMC Genomics, researchers used a pictograph to illustrate the relative percentage frequency distribution for nucleotides in DNA, using images of the nucleotide letters instead of tables. Pictograms can be effective at summarizing everything from health facts by the state to nucleotides in a human DNA sequence. In addition to tables, data can also be displayed through graphs. Most often, graphs and tables are equally effective in summarizing frequency data. However, graphs have the main advantage of being more visual and less intimidating than tables in many cases. There are many ways to graph distributions of continuous data. Some of them are histograms, frequency polygons, and ogivs. We'll look at each of these. A histogram is a graphical display used to summarize the frequency of continuous data that are distributed in numeric intervals. It's used to summarize group data. The histogram distributes the intervals along the horizontal scale, x-axis, and lists the frequency of scores in each interval on the vertical scale, y-axis. There are 3 rules for constructing a histogram. Rule 1, a vertical rectangle represents each interval, and the height of the rectangle equals the frequency recorded for that interval. Rule 2, the base of each rectangle begins and ends at the upper and lower boundaries of each interval. This means histograms cannot be constructed for open intervals. Rule 3, each rectangle touches adjacent rectangles at the boundaries of each interval because the data are continuous. A frequency polygon is a dot and line graph used to summarize the frequency of continuous data at the midpoint of each interval. In this type of graph, a dot is plotted at the midpoint of each interval, and a line connects each dot. To calculate the midpoint, add the upper and lower boundary of an interval and then divide by 2. Most often, a histogram and a frequency polygon are equally effective at summarizing data. Researchers make the choice based on how they prefer to present their data. An ogive is a dot and line graph used to summarize the cumulative percentages or cumulative frequencies of data. In an ogive, a dot is plotted at the upper boundary of each interval because this point represents or contains all of the scores in that interval. Each dot represents the cumulative percentage of scores at each interval, and a line connects the dots. A stem and leaf display, also called a stem and leaf plot, is a graphical display where each individual score from an original set of data is listed. It can be used for discrete or continuous data and is particularly useful with smaller data sets because each individual score is preserved in the display. The leaf is the number or numbers located to the right of the vertical line in a stem and leaf display. The stem is the number or numbers located to the left of the vertical line. In the display, the data are organized such that the common digits shared by all scores are listed to the left in the stem, with the remaining digits for each score listed to the right in the leaf. To construct a stem and leaf display, first you have to recognize the beginning digits of the scores in your data. Then you reorganize the data so that every number with the same first digit is placed in the same row. You can place the first digit in its own column to ensure it's never repeated in a single row. In a stem and leaf display, the leaf lists the last digit or digits for each number in each row, and the stem lists the first digit or digits for each number in each row. The names stem and leaf actually derive from their appearance in the display. There are several ways to create stem and leaf displays depending on your data. Stems can be more than one digit, and in some cases, leaves can have more than one digit as well. Stem and leaf displays are similar to histograms because both show the shape of a distribution for continuous and discrete data. However, the stem and leaf display lists the actual scores in the distribution instead of frequencies. This convenience, researchers can read the raw data immediately from the display, usually in ascending order. The only information lost is the order in which data were originally obtained. Researchers often measure discrete variables, which are variables measured in whole units or categories. Examples include the number of traffic accidents or the number of college graduates. These variables are considered discrete because they are measured by counting one at a time. Researchers also measure categorical variables, which vary by class. Examples include race, gender, and marital status. Discrete and categorical data are graphed differently than continuous data because they are measured in whole units or classes and not along a continuum. Two types of graphs used for discrete and categorical data are bar charts and pie charts. A bar chart or bar graph is a graphical display used to summarize the frequency of discrete and categorical data. The data are distributed in whole units or classes, such that a vertical rectangle represents each whole unit or class. The height of the rectangle equals the frequency recorded, and each rectangle does not touch adjacent rectangles. The key difference between bar charts and histograms is that in bar charts, the bars are separated from one another, while in histograms, the vertical rectangles touch each other. The separation between bars reflects the separation or break between whole numbers or categories being summarized. This is why bar charts are appropriate for discrete and categorical data. To construct a bar chart, list the whole units or categories along the x-axis and distribute the frequencies along the y-axis. Bar charts have two main characteristics. Each class or category is represented by a rectangle, and each rectangle is separated along the x-axis. The bar chart is essentially a histogram with the bars separated, which makes it appropriate for summarizing discrete and categorical data. A pie chart is a graphical display in the shape of a circle. It's used to summarize the relative percentage of discrete and categorical data into sectors and is used almost exclusively with discrete and categorical data. You can think of pie charts as slices or pieces of data. To construct a pie chart, first distribute your data as relative percentages. Then convert this distribution to the pie chart by finding the correct angles for each slice of pie. Since a complete circle has 360 degrees, multiply each percentage by 3.6 because 100% times 3.6 equals 360 degrees to find the central angles of each sector. The total of all angles should equal 360 degrees. A sector is the point of the portion of a pie chart that represents the relative percentage of a particular class or category. To find the central angle for each sector, multiply each relative percentage by 3.6. This concludes Chapter 2. Here are a list of your Chapter 2 summary takeaways.